Last thing to look at with polynomials is this relationship between roots and coefficients. Now, we have seen the idea previously with just the quadratics, but now we're going to expand on that idea to any polynomial. So if you remember with the quadratics, the general one of course being ax squared plus bx plus c, we said the sum of the roots will be minus b on a, and the product of the roots would be c on a. And that's why when we're trying to factorise quadratics, we say, oh, what adds together to give the middle number, or b, and what multiplies together to give c. Now, a cubic, so general one being ax cubed plus bx squared plus cx plus d, a similar thing happens. The sum of the roots is still minus b on a. But notice b is now the coefficient of x squared and a is now the coefficient of x cubed. Instead of just the product of the roots, if we take all the pairings, if we take the roots two at a time, so it is still similar to the quadratics because there was only one pairing two at a time, and that was alpha beta. But when we come to a cubic, there's now three possibilities. You could have alpha beta, you could have alpha gamma, or you could have beta gamma. And the sum of all those, so the sum of the roots taken two at a time, still remains c on a. But we now have an additional one, because we can now have three roots grabbed together, because a cubic, of course, has three possible solutions. And you can see how the pattern goes. It's now minus d on a. And we can keep going like that. It just goes minus, plus, minus, plus, minus, plus, and just the coefficients of the individual terms over a. So if I wanted a quartic, so power of 4, again now a represents the coefficient of x to the 4, b x cubed, cx squared, and so on. We now have four roots, and the sum of those roots will still be minus b on a. If I grabbed all the possible pairings, and there's 6 of those, that would be c on a. If I grabbed all the possible triplets, so grabbing 3 at a time, and there's 4 of those, we get minus d on a. And now we've got an additional one where if we grab all 4 of them at once, grab all 4 of them, but that now will become positive e on a. As I say, we could keep going with that pattern. So to generalise it, for any polynomial, so a will always be the coefficient of the leading term. And then we'll go down B, C, D, and the constant will be whatever the last letter ends up being. Sum of the roots one at a time. So here's a shorthand way of writing it if you've got a lot of roots. So instead of going, oh, alpha plus beta plus gamma plus delta plus whatever, we can use our sigma notation for sum of, and we just put one root there. And traditionally, we just put the first one, alpha. So that's saying sum of the roots taken one at a time, that will always be minus b on a. Sum of the roots 2 at a time will always be c on a. Sum of the roots 3 at a time will always be minus d on a. Sum of the roots 4 at a time will always be e on a. And I can keep going and keep going with that pattern, depending on how many roots the polynomial has. Now, you might remember back in the quadratics, there was a standard question where they like to say, oh, what was alpha squared plus beta squared? And we rewrote it and we said, oh, well, alpha squared plus beta squared, that's alpha plus beta all squared minus 2 alpha beta. That pattern also remains for all polynomials. So if I want to find the sum of the roots one at a time squared, that will always be the sum of the roots one at a time all squared minus 2 times the sum of the roots 2 at a time. Now, it doesn't matter what the degree of the polynomial is, that will always be true. Okay, let's have a look at some examples. So I've got a cubic, so we've got 3 roots, alpha, beta, and gamma. It's just a random question. Find the value of 4 alpha, 4 beta, 4 gamma minus 7 alpha, beta, gamma. So we can find the sum of the roots one at a time is 5 on 2. I don't really need 2 at a time for this question, but I'll find it anyway because we may as well, in case the next parts need it. So 2 at a time would be minus 3 on 2, and 3 at a time is minus 1 on 2. So for part A, I've got 4 lots of the alpha, beta, gamma, so 4 lots of 5 on 2, minus 7 lots 3 at a time. So really, same sorts of questions we saw in quadratics, but now there's more roots we have to deal with. What about the reciprocal? That was a nice standard question they had in the quadratic one. Same idea, let's turn it into an algebraic fraction. So the common denominator will be alpha, beta, gamma. So we got that, sum of the roots 3 at a time. The numerator turns out to be sum of the roots 2 at a time. So subbing into that one, we get our answer of positive 3. Pretend that's a positive there. Okay, that's not there. There's the standard one I was talking about, the alpha squared plus beta squared plus gamma squared. So yeah, that will be alpha plus beta gamma all squared, minus 2 times sum of the roots 2 at a time. So subbing into that one. There you go, 37 on 4. Ooh, a very old HSC question. So again, it's a cubic. They've told us there's 3 roots. We're calling them alpha, beta, and gamma. So the first question is a bit of a gift mark, really. So we say, thank you very much. But you can see a lot of people would have made a very simple mistake. Yeah. Notice there's no x squared in there. So the sum of the roots is actually 0. Because b on a minus b on a, there's a lot of people would have put 3 for that answer. So. Okay, second question, the product of the roots. We goes minus plus minus, so it'll be minus 1 for this one. And the reciprocal question. So that's 2 at a time over 3 at a time. Well, we've worked out 3 at a time. Haven't worked out 2 at a time yet. So that'll be minus plus plus. So it'll be minus 3 will go on the top and minus 1 on the bottom. Positive 3. One a little bit more recently, still a long time ago now, 11 years ago. 2003 question. We are told that 2 of the roots are reciprocals of each other. And we've got to find out what k is. So instead of letting the roots be alpha, beta, and gamma, I'm going to let them be alpha, 1 on alpha, and beta. Now, the first thing, I'm going to do product of the roots 3 at a time. Because I know the alpha and the 1 on alpha is going to multiply to give 1. And so I will actually find one of the roots straight away. So beta is negative 3. Now, we know negative 3 is a solution. We just found a solution. So I know polynomial negative 3 is equal to 0. So I can sub that into the equation and work out k. That, I think, is probably the quickest way of getting k. You could, of course, play around with and go, oh, well, let's look at some of the roots 1 at a time, some of the roots 2 at a time, create simultaneous equations. I think a lot of people would have probably tried that. But once I know a root, well, we can use our factor theorem and say, oh, well, if that's a solution, I know that's going to be 0. 2006 paper. So this time we've got a few pronumerals there. X cubed plus rx squared plus 6x plus t. We've been told the zeros are 1, alpha, and minus alpha. Find the value of r. Well, in this case, 1 at a time is going to be handy because when I add them 1 at a time, the alpha and the minus alpha will cancel. So I'm going to have 1 plus alpha plus minus alpha is minus r. So r turns out to be negative 1. So there's the first part of the question. Find the value of s plus t. Which one to do first? Well, probably going to have to do both of them because I've got to get s and t. So 2 at a time, I've got 1 times alpha, 1 times minus alpha. Again, they're going to cancel. I'll have alpha times minus alpha. So I know s is minus alpha squared. Let's do 3 at a time. That's the one we haven't done yet. So 1 times alpha times minus alpha. So minus alpha squared, oh no, positive alpha squared will be t. Well, now I can just substitute in for alpha squared.
So can you put 1 into the polynomial?
Say that one again.
Put 1 into the polynomial x.
There's a good idea too. Yeah, you could have done that. You could have said, let's substitute 1 into the polynomial because it's a solution. So we know polynomial 1 is equal to 0. And so we would have got 0 equals 1 plus r plus s plus t. But we just worked out r was negative 1. So again, we'd come up with s plus t equals 0. Yeah, that's a good solution. All right, so 4F, let's just play with our roots and coefficients.